There, everyone. This lecture will consider Fourier transform. In our previous lecture, we saw a necessary and, let's say, and a sufficient condition for the Laplace transform to converge to the Fourier transform. And we saw that the Fourier transform can be or may be considered to be equivalent to the bilateral Laplace transform calculated along the j omega axis. That is, if we have the bilateral Laplace transform given as s of x, taking limits of integration from infinity to infinity, s of t, epsilon st dt, for all values of x, taking all values from sigma to j omega, where sigma is the damping factor and omega is the angular frequency of L07, say frequency in radians per second. Then this is the same, taking the integral to limit from infinity to infinity epsilon s sigma j omega t dt. Then we have negative infinity to infinity s of t in sigma t j omega t dt. Then see that s of s is the same as the integral of s of t. So sigma t j t dt, such that when the damping factor reduces to 0, then the Laplace transform will reduce or will tend to the Fourier transform given as integral of s of t of epsilon 0 j omega t t, which is the same as infinity s of t times 1 t t, or we have integral s of t j t t, okay, for which the bilateral Laplace transform extends to the Fourier transform, which we could express as s of omega. Okay, good. And call that omega is the same as 2 pi f. So s of omega can also be expressed as s of f, which should now be negative integral s of t epsilon 2 pi ft dt. There you will see that this condition holds when the bilateral Laplace transform is investigated along the j omega axis. And you see that for bounded signals, they always include the j omega axis within the region of convergence. Then you see it would be more convenient, therefore, to speak of Fourier transform rather than figuring out ways to estimate the region of convergence after taking the Laplace transform. So, in general, the Fourier transform extends the class of signals that can be analyzed in the frequency domain. But by further investigation of this relationship, now referred to as the Fourier transform, you will realize that the Fourier transform is said to be strictly dependent on the frequency. Okay. So hence, the Fourier transform is a tool used to switch a signal from the time domain to the frequency domain to enable the analysis of the frequency content of the signal. While the Laplace transform is mainly used for system analysis, Fourier transform is used for signal analysis. So we can conclude that the Fourier transform is used for signal analysis. So Fourier transform is commonly used in signal processing. Okay, signal processing. Now let us look at the inverse Laplace transform. So the inverse Laplace transform follows directly such that s of t is the same as 1 over 2 pi integral to infinity s of omega epsilon j t dr. And from this, we can therefore conclude that the Fourier transform pair exists, just like in the case of Laplace transform. Now, this is the inverse Fourier transform. Now, note that the inverse Fourier transform shows that a continuous time signal, s of t, can be represented as the weighted sum. This is a sum integral, and this is the weighting on of the complex exponential epsilon j omega t. Okay, and recall from your trigonometric identity that epsilon j omega t is the same as cos omega plus omega t plus j sine omega t. Okay, so in other words, this is a complex exponential while these are sinusoids. Okay, so The inverse Laplace transform is therefore seen as the weighting, or better say the sum of the weighted complex exponentials. Now, since the inverse Laplace transform is given as a function of the angular frequency, should we desire the frequency representation, then S of t will be the same as 1 over 2 pi, negative infinity, infinity, S of f, epsilon, j 2 pi, omega 2 pi ft, d 2 pi f. Okay, so let's bring this out. So that will be 2 pi over 2 pi, infinity to infinity, S of f, epsilon j 2 pi ft, df, which is the same as negative infinity to infinity, S of f, epsilon j 2 pi ft df. So the inverse Laplace transform is therefore either of this form. Omega, so t omega, or this form. Good. So if we take the inverse Laplace transform, which is a function of the frequency, sigma df. Now, by using the Riemann sum to express the inverse Fourier transform, you see that S of t is the same as from negative infinity, so that will be x of f s of f negative infinity epsilon j 2 pi f negative infinity t plus all the way to s of f naught epsilon j 2 pi f naught t plus s of f naught epsilon j 2 pi f naught t plus s of f2 epsilon j 2 pi f2t all the way to finite value s of f t to df. Now, delta f is the difference between the upper band frequency and the lower band frequency for all values. Now, you will notice that the weight S of k is different for each frequency sinusoid, and it is a complex quantity. So in other words, S of F minus this is not the same as S of F naught. It's not the same as S of F1. It's not the same as F of S2. It's not the same as S of. Okay, and these are all complex quantities. They are complex quantities, right? And like we mentioned in our lecture on the classification of systems, once a signal is multiplied by a complex quantity, the magnitude and phase of the signal is altered. So now that the exponential sinusoid is multiplied by a complex quantity, therefore S of Fk will give each complex exponential component or sinusoid a magnitude and phase. So in signal processing, the inverse Fourier transform is used for the recovery of signals by utilizing the magnitude and phase information stored in the original signal. So, if we consider an LTI system, say where the input is S of t, LTI, so Ti divided by h of t, then the output is y of t, which is the convolution between S of t, h of t. Now, should we take the Fourier transform of S of t, S of omega? Now, Fourier transform h of t will give us h of omega. Then, Fourier transform of the output will give us y of omega, the same as S of omega, h of omega. Now, since the output of the LTI system is defined as the product of the input spectrum and the system response, we can therefore define this properly, designate properly, that is y of omega is the same as S of omega, h of omega. Recall that convolution, just like we mentioned in our previous lecture, in the time domain will result in multiplication in the frequency domain, right? So here, y of omega is the output spectrum, then S of omega is the input spectrum, H of omega is the system response. Recall that these are expressed, just like we mentioned earlier, in terms of their magnitude and phase. So notice that the output spectrum here is scaled, or better still, is the scaled version of the input spectrum. So the input spectrum is therefore seen to be scaled by the system response, making the LTI system act more like a filter. Okay? So, more like a filter. Because the system itself scales the input by some parameters. So that is the LTI system. It's more like acts as a filter on the input signal. So since the input signal is scaled by a complex quantity, as previously established, the frequency response can be designated by the magnitude and phase. And the frequency response is h of s. So in other words, h of omega rather. Now h of omega will now be designated by the magnitude, which is mod h of omega, and the phase j phi h omega. So in this case, the mod of h of omega is the magnitude response. This is the magnitude response. That's still could say the amplitude response, okay? Y phi h omega is the phase response. So in a similar vein, the input spectrum S of omega can also be designated by the mod of S of omega S of omega epsilon j phi x omega, and the output spectrum can be designated as the mod of y omega magnitude epsilon j phi y. So here the mod of S omega and the mod of y omega are the magnitude spectrum for the input and output respectively. Y phi x omega and phi y omega are the phase spectrum for the input and output respectively. So you should note that filters are used to designate systems that exhibit some sort of frequency selectivity, okay? Because at this point, what we are dealing with are the frequency spread in the system, okay? So that is these filters now, they are filters because they are able to pass certain frequencies while rejecting or attenuating other frequencies. So it means the parameters of H omega must be selected carefully. Okay, let us consider a practical filter. So let us consider the practical, say, low pass filter. Okay, see, so this is the output. So we feed the input through this. So let's assume the input here, the signal is S of t, and the output is Y of t. Okay, so bottom line is we want to take the Fourier transform of the system function. Okay, and in this case, we'll have to figure out the response of the system. Okay, now let's omega, that's for S equal to j omega, then we have the Laplace transform. So what we want to figure out here is h of, okay, that's the response. That's the response of the system. The frequency response, okay? The frequency response. And from the frequency response, we can tell the design of the system because this parameter acts on the input, okay? So in other words, should we have certain input X, then we want to achieve a desired input or output. Let's say desired output. So, and Y of omega is our desired output. So it means this input will have to go through a system that will act on it with H omega to produce this desired output. So in other words, the H of omega acts as the filter, okay, such that H of omega, S of omega will now be the same as the output. Then this response can be estimated by taking the ratio of the output to the input frequency spectrum. Okay. So in other words, we want to figure out the ratio of the output to the input and take the Fourier transform, and there we go. So in this case, we can actually check out the KVL around this loop. And once we do that, we have minus x of t, so by passive sign convention, plus minus, plus IR plus y of t is equal to 0. So this is our first equation. And now the current relationship between this capacitor and the output is given as I equal to C dy of t dt. That's our second equation. So if we put 2 into 1, put 2 into 1, what do we get? So S of t is the same as RC, put this into this, RC dy of t dt plus y of t is equal to 0. So that's minus S of t. So this is plus RC plus 1. RC, if we bring up y of t, because we want to relate y of t and s of t, so that's d dt. RC d dt plus 1 y of t is equal to 0. So if we rearrange this, so 1 plus RC d dt y of t is the same as s of t. Okay. So if we take the ratio between y of t and s of t, that is, if we divide through s of t, then we'll have 1 over 1 plus RC d dt. Now, this is in the time domain. So, let's look at this. Let's change the color. This is in the time domain. Okay? So, if we take the Fourier transform, then we can progress to the frequency domain. Then we already know that the ratio of the output spectrum to the input spectrum will give us the frequency response. So the frequency response h of omega will be the same as y. The Laplace transform, the Fourier transform of y of t is y of omega, and the Fourier transform of s of t is s of omega. That'll be 1 over 1 plus j omega RC. Now, this is the frequency domain. But recall for an RC circuit, the time constant for an RC circuit tau is the same as RC. Okay, and we know that the time constant is the time in seconds in which the voltage across the capacitor would reach its final value if its original state of change is maintained, right? So if that's what it is, then we can rewrite this, the frequency response, to be the same as y of omega over s of omega. It's the same as 1 over 1 plus j omega tau, right? Now, but also for the RC circuit, the time constant is the same as the inverse of the negative 3 dB angular frequency. That is, RC circuits, the time constant tau is the same as the inverse the negative 3 dB frequency omega naught, for instance, such that tau is the same as RC for the 1 over naught, such that, so that the frequency response h of omega will now be y of omega over s of omega, now be the same as 1 over 1 plus j omega divided by omega. Okay. Fine. So hence, from this expression, now we have been able to establish that the frequency response of the low pass filter is the same as 1 plus j omega divided by omega naught. And then from this, we can estimate the magnitude. So the magnitude, or better still, amplitude response mod of h of omega will be the same as the square root of the square of this parameter. So that will give us 1 over 1 squared is 1 plus omega divided by 1 squared. Then take the square root of that. Why the phase response? The phase response phi of omega, same as tan inverse that, so take tan inverse omega, right? So as we take, so perfect. So should we plot the magnitude plot? Will look something like this. Have half power bandwidth somewhere here. 0. This is 2. And this is 1. Then this is the magnitude plot. Call this is the same as 1 over tau from RC. This is then the phase plot something like this. So at this point, 5, 4. At this point, 5, 2. So 5, 4. So 5, 2. So then this is the phase plot. So see that all frequencies above the cutoff frequency is a roll off anyway. Are removed. Okay, so perfect. So well, there are a couple of other filter designs and all of that. Well, the purpose, all we wanted to show here is the direct application of the Fourier transform. Okay, so some other, let's say, idealized filters. Okay, let's say typical filters. We have the low pass filter. And the model looks something like this. This is the cutoff frequency. 0, for instance, is 1. So this removes all frequencies, or better say frequencies above f sub c. Okay, so it passes only the low frequencies. Okay, then for the high pass filter, looks something like this. This is 1, for instance, is 0. So it removes all frequencies below the cutoff. So all the low frequency components are suppressed while the higher frequency values are passed. Then we also have band pass filters. So they're something like this. So it is F1, it's F2, this one is 0. So it removes frequency information outside the band of frequencies F1 to F2. And we use this in, let's say, your radio unit, okay, for tuning from one channel to another. It's very useful there. And then we have the notch filters. Okay, so they remove all frequencies between F1 and F2. Okay. So, in summary, we can say that since Fourier transform shows the frequency content of the signals, the process of selectively removing or altering part of the frequency content to produce the desired signal is featuring. So we say S of t goes into system factorized by h of f, then we get y of t. So once we take the Fourier transform, then we have y of f is the same as h of f, s of f. Okay, so in other words, the shape of h of f is carefully chosen to alter s of f in a desirable. Okay, so in other words, h of f is referred to as the field. Good. So let us look at some verifiable properties of Fourier transform. So, well, these are some of the verifiable properties of Fourier transform. So for linearity, the sum is equivalent. The frequency domain, we have duality. We already explained that the convolution in time domain is multiplication in frequency domain, and multiplication, which is the product, multiplication, which is the product in time domain, is a convolution in frequency domain. The frequency time shifting, then this frequency shifting. And recall that in the last example we had, the Fourier transform of d dt was j omega, okay, which is this, and all the way. So let us consider a few examples. So we want to show that the Fourier transform of a rectangular function is the same as the sinus cardinalis function, okay? So we know that a rectangular function, rate of x, rate of t rather, let's say s of t is the same as rate of t, defined as 1, 0 for mod of t less than a, 0 for mod of t greater than a. Then we have something like this. This is 1 to this s of t. This is t. This is minus a. This is a. Now, I want to show that the Fourier transform of this function is going to give us something like this, which will be sine pi x over pi x, in that form. Okay. Now, this 3. Now, we know that Fourier transform is given as the integral, taking limits from negative infinity to infinity, s of t, so minus j omega t dt. Now, this is going to give us this 1, the s of t is 1, between these limits, minus a 1 times epsilon minus j omega t. And this is going to give us minus 1 over j omega to bracket epsilon j omega t minus a to a. This will be minus 1 over j omega epsilon minus j omega a minus epsilon minus times minus, that will give us plus j omega. So if we open up this bracket, so that will be minus 1 over square root j omega epsilon minus j omega a plus minus times minus plus 1 over j omega epsilon j omega a. So this will now, if we rearrange, so that will be this expression minus this expression. So that will be 1 over j omega epsilon j omega a minus this epsilon minus j omega. Okay. Now, if you we compare this expression with the trigonometric identities, recall that epsilon plus or minus j omega, for instance, or let's say omega a, let's put it in this form, be the same as cos omega a plus or minus j sine omega a. And then cos omega a in Euler form be the same as 1 over 2 to bracket epsilon j omega a minus epsilon minus j omega a by sine a be the same as 1 by j2 epsilon j omega a epsilon j. So these are trigonometric identities. So if we compare this identity with this, we see the closest is this. It's closest. That's the closest, right? Sine omega. So if we compare, we know that our Fourier transform is the same as 1 over j omega e j omega a minus epsilon j omega a. So let's write this. Now we want to compare with, we want it to be equivalent with sine omega a, which is the same, which is equivalent to 1 is equivalent to 1. That's this. This is the same as this. So this is the same as j2 epsilon j omega a minus j. Now you observe that this part is the same as this part, but this part and this part are equal. So we need to make that equal. So for us to do that, we don't have a 2 here. So it means that to truncate this 2, so it will be equivalent to this, we have to multiply by 2 here, or have to multiply by 2 here. So that truncates this, so it means this and this are equivalent. So, but still not equivalent to this. For it to be equivalent to this, we now have to divide. We have to divide by omega. Then this also have to divide this by omega. So like this. So I have to divide this down. So it means this expression is now equal to this expression. Good. So in other words, can now say that S of omega is equal to 2 sine omega A divided by omega. But recall that sinus cardinalis is the same as sine pi A, which is sinc, over pi A. So these parameters has to be equivalent. And for us to do that, it's simple. We can multiply both sides by A. We can multiply and divide by A. So if we multiply this A over A, then we have the same expression. So then that's fine. So once we truncate these two, we still have the same thing. So we're scaling both the numerator and the denominator by the same parameter, which gives us the same. So it's really not scaling. It's not scaled anyway. So this will now give us 2A dot sine omega A omega. So in other words, we have been able to show that given a rectangular function, this is 1 minus A, 0, the time domain, once we take the Fourier transform, the reverse is the inverse Fourier transform, then we are going to get a sinus cardinalis function, sinc function. Something like this. This is S of t. This is S of omega. Now, amplitude is 2A. This is omega. And it's going to have pi over A minus pi A minus 2 pi over A, 2 pi over A, and so on. Okay. Okay, so meaning the Fourier transform of a rectangular function is a sinc function. Okay, let's consider some. So let's assume we are given a system described by dy of t dt plus 2y of t is the same as s of t plus the x of t dt. And now what we want to check out is first the frequency response of the system, h of omega, and the inverse Fourier transform of the system. Okay, so I have this. Now that we are given the y of t dt, so y of t same as s of t plus the s of t dt. So if we take the Fourier transform of this Fourier transform, call that d dt will give us j omega, right? The frequency domain. So this will give us j omega. Y of t will give us y of omega plus 2 y of omega is the same as s of omega plus j omega s. So this will be the same as j omega plus 1 plus 2 rather plus 2 y of omega. This is x, right? This will be 1 plus j omega s of omega. Now we already know that the frequency response h of omega is the ratio of the output spectrum to the input spectrum. So this is going to give us 1 plus j omega divided by 2 plus j omega. Okay, perfect. So how do we resolve this? Now, it's simple because want to now this also can be rewritten as, let's say 2 minus 1 is the same as 1. And then we may be able to rewrite this in the same format, say 2 plus j omega minus 1 divided by 2 plus j omega. Yeah, this is the same as this. So 2 minus 1 is 1. That's the same as this. So then we can expand further to say that 2 plus j omega divided by 2 plus j omega minus 1 divided by 2 plus j omega. So by writing the same thing. So this now will be the same as 1 plus 1 over 2 plus j. Okay. So in other words, the frequency response of the system is 1 plus 1 over 2 plus j. Now, just like in the case of Laplace transform, so by using the Fourier transform pairs, the inverse Fourier transform can be derived accordingly. So the Fourier transform, so we have h of omega is the same as 1 plus 1 over 2 plus j omega. So if we take the inverse Fourier transform here, so this will be h of t equal to 1 is going to give us Dirac delta function. Then this gives us epsilon minus 2t of t. So at this junction, I think it will be sufficient to provide a list of some verifiable Fourier transform pairs. So these are some of the verifiable Fourier transform pair. And which of them did we use now? Okay, we resolved last example. Okay, for the rectangular function, red function. Okay, that's this. Okay? For the red function. Okay. The red function, if it's this, results in a sinus cardinalis function. Okay, and for should we have a sinus cardinalis function, a Sinc function, that's Sinc function, then the Fourier transform a rectangular function. And for the Dirac delta function, the Fourier transform is 1. That's the same goes for that. And then, meaning this output, we are going to get something like this, because this is just a spike, right? This is a direct data function. So this is one, right? Good. And when we have this in the time domain, then the Fourier transform give us a direct data scaled by 2 pi. So on and on. And here you see that for a cosinusoidal function in the time domain, what we see, the spectrum you see after Fourier transform is a spike, a time-shifted impulse. Yeah, that's what it is. So it's time-shifted impulse. So you see impulses, that's minus f naught is 0, and this is f positive f. So what you will see in the frequency domain are sets of impulses. The same for the sine wave. So once you take the Fourier transform of the sine wave, so you're going to get so this is even and this is an odd function, okay? And then on and on. So with these Fourier transform pairs, one could easily derive the inverse Fourier transform. Okay, I think this is a good place to stop, and hope to see you in our next class. Bye for now.